Okay, what I'm going to do is just briefly recap where we ended up last time with the force laws. And that put us in a good situation because I've been making this little diagram of the, say, 4 ingredients that go into a Newtonian approach to mechanics and how we've mapped this into economics, right? So we had a definition section where I've defined the quantity demanded as a change in an account balance, all right? The velocity is a change in position, all right? And we've also kind of, doesn't really fit, but that's the way Newton did it, defined the quantity demanded, not defined it, but posited that the quantity demanded is proportional to the price, okay? So that's your demand line. And this in Newtonian mechanics is just it's called the definition of momentum. This is P is M times V, but I wrote it the other way around. It's more logical that way. All right. And then we spent a good amount of time getting to the counterpart of this one, namely that the price itself, the rate of change of price, is an economic force. So an economic force represents a want or an incentive or a desire or you name it, all kinds of things, okay, a motive. And the way you express that in economics everything has a price, has a value, is by upping or lowering your price. That's what this says. And in fact, it says as soon as you see some price change, you know there's a force going on. All right? Now, where do these forces come from? These economic forces, they can come from all kinds of things. These are specified by what we call force laws. All right, so they're not really laws, they're constitutive equations. There's a better word for it. It tells you how a force can be related to other quantities, in particular when it's related to a stock. Let me find the if it's related to a stock, we can measure scarcity. So the more you have in stock, the less scarce it is. And the less it is you have in stock, the scarcer you'll feel it is. All right. So this is what you would call the force of scarcity. The way it works is normally, if this is the spring force, we would write it as a positive force. So it's the force that you have to apply on the spring in order to extend it. But the force the spring applies is a reaction force, so it goes the other way. All right? Okay. So that force, the negative of this thing, is called the scarcity force. And if you write it like this, really you have the negative of the scarcity, which is the convenience. Okay? So the more you have, the more convenient it is for you, and the more you end up paying for it, okay? Because you've got to pay for that convenience, or the inconvenience of not having it. So if you loan something to somebody, he or she that has borrowed it owes you something, namely the inconvenience that you don't have it, okay? That's one of the origins of what goes into the rate of interest. There's going to be lots of stuff going in there, but this is one of them, okay? Now, when I write V is epsilon times P, or P is M times V, that's always a linear law, all right? Unless you're doing relativity, and even then, the mass does not depend on the velocity, okay? It may depend on time, but that's a different matter, okay? But it does not depend on the velocity. So, if I write the price is the price of electricity times the quantity demanded, it cannot be that this thing is a function of V. It's a constant, okay? All right? But these type of laws, there's no problem, okay? So this K can depend on Q. So for instance, this law could look like F is, I don't know, some other K, C times Q squared, right? And you'll have a K, which is C times Q. There's nothing wrong with that, okay? And in fact, So in fact, this is what you typically see. A linear spring in mechanics is something exceptional, all right? So you find it with a, like here, huh? So this was a linear one. And this one is only linear in this area, and then, this is a typical spring you'd have or a beam that you would stretch, there's this elastic area, and then you go through this plastic area, and then it breaks and it just kind of goes down. Now you have something similar in economics, okay? So for small changes in the stock, now the convenience or the scarcity you measure will be linear with that, okay? It will depend on it, but in a linear fashion, all right? Huh? But when you get huge amounts, you're not really, you don't care that much anymore. Huh? So what you'll see is a typical flattening down of this line. At a certain point, you get so sick and tired of having this stuff lying around, it may even become worthless, all right? So what I want to say with this is this typical elastic plastic breaking behavior that you see in elastic beams and elements, you see here too. There's actually, for those of you doing finance, if this is an amount of money, right? So these are just cash you have on the bank or I don't know what. Then usually when you have more, the desirability, it's desirable to have more and more money, all right? Huh? As a liquidity buffer, this is this Keynesian theory. But it doesn't go on like this. So at a certain point, you call that your liquidity, how much cash you have on hand. At a certain point, extra liquidity, people don't care anymore. And that's called a liquidity trap. You will probably know this. Huh? It's called a liquidity trap. So Keynes had this idea that people want to store money for transactional motives and be able to do something with it. If you have some money at hand in your wallet and you want to buy something, you can just go do it. You don't have to go beg around for some money or get it from somewhere. All right. But then they found out that if you give them too much, they stop caring. And it's called a liquidity trap. They use this for stimulus and stuff like that. Anyway, it's just I'm saying this more to have you start thinking of how to take things from engineering and then see that you can apply almost everything, I feel, to economics with enough of imagination. Okay? Here I have another one. This is, for Shell, we once did a project, and they have these big storages, and here, big silos, and have oil up to there, and they have some level at which they want to keep it here. And then it goes up, but then they have this thing with hard stop. At a certain point, you keep whatever you want, you can't put any more in it, right? So you'll see that these things, they go like this, they go up like that, Huh? It's really, it's like when your capacity is limited, you just can't stuff anymore in. And then the force just goes way up, right? So we'll have the same thing. I mean, physically, it's the same thing, okay? And then there'll be some convergence here, where this is some maximum. Okay? So I don't think everything is linear. Like in engineering, it isn't. Okay. But this one is always linear, the lower than that. After this one, we'll do something with rotations, and we'll do a little bit of the relativistic analog with surfaces, and we'll see that we can get these curved ones when there's a limit to how much the quantity can be demanded or supplied. But for now, the Newtonian thing, that's the one that's always linear, all right? If you measure something else, there must be another force that you're just not seeing, okay? I measure force. Don't go and monkey with the price elasticity. Okay, so there we are. So I see everybody nodding, so I'm assuming there's no questions about this anymore. All right, so we have this, and now, if you have this in place, you could go ahead and start solving problems. But I don't want to do that, because there's two more concepts that are really worthwhile developing before we give you examples of how to do it. And they are parallel to the two concepts that you have in mechanics that you will also learn in a dynamics course. And the first one is that of energy, all right? And the second one is that of equilibrium. So today I want to talk about the analog to energy. And you will all agree that when you solve these problems in mechanics, you just know what energy is, and you mix and match that with forces and momentum. Okay. Now the history of energy is kind of interesting, because for a long time, people didn't really see the difference between energy and force and momentum. Okay. Force probably they did, although they called energy the vis viva. And nobody was really clear, what that was. Was that a force? Huh? Something that the vis was a force that gives life. Okay? Was it a real force? Was it a different force? What was it? Okay? Huh? Now the word energy, I believe, already existed before our era, right? Before the birth of Christ. So Greek philosophers talked about it, but it wasn't really tied into mechanics until much, much later. I think the 19th century, that Young or somebody said, okay, we can call this energy. Before that, they had weird names for it. And there were discussions whether energy was this or this, and nobody was really sure. And it was slowly settled that it turned out, it's actually an experiment by a Dutch guy, Zonde, who measured, what the impact was of a ball falling. And then a French lady, Emily du Châtelet, kind of figured out that this was the formula, I believe. It's a little bit murky. I couldn't really figure out who finally ended up with this. I know Leibniz did this. Schradersonde did the experiments where he would show that there was something going on that you could measure, so you didn't have to guess it, and then somebody put it together, okay? But the amazing thing about the Newtonian approach is you can define energy and the various forms all just using Newtonian mechanics. You don't need any more assumptions, nothing. Okay, and that's what we're going to follow here. Okay? So, the Newtonian approach gives us two variables. Here they are. A velocity and a force. A quantity demanded and the desire we have for it. Right? And two variables that belong to that, if you integrate them, your balance and the price you assign to a unit. Okay? This is kind of a pair, you see? These ones we call them power variables, and these we call them energy variables. And this coupling then says how they relate to each other, and you can do the dynamics. But the concept of energy comes from this pairing of these two variables, okay? And here is the idea. Let me first say it mechanically, and then I'll say it economically. So suppose you have some kind of force or voltage, that's the parallel, but no current is flowing. What's going on? See, the thing is, there's not much going on. There's just a voltage. Huh? Okay? So, you can't drive a car with it, you can't run a computer with it, you can't do anything, you just have this voltage. Congratulations. Now suppose you have a current, so there's just a current going, right? Or you have a velocity, there's just this thing going with velocity. Okay. You can make that velocity zero if you take the right inertial reference frame. In fact, you can make that voltage zero by defining your earth to be exactly that voltage. Okay? Huh? So, there's really nothing going on. It's just, all we did was just define a bunch of terms But, we haven't done much yet. We haven't been able to show how this relates to anything real that we can experience, okay? Now, if I stick my fingers in that thing, of course I'm going to get a shock. But that shock will only happen if a current goes. If there's no current and I have an insulator, then still nothing is going to happen, all right? So, you all know that what I got to do is multiply the velocity by the force in order to deliver some power, right? And if I do that over time, then I transfer some energy from one place to another, and then really something happens, okay? Then I can run a machine, all right? Huh? So you see the idea of energy is sitting right here. All you have to realize is that you've got to multiply these two together, all right? Huh? That's the trick. Now, the same is true in economics. So, suppose this is your quantity demand. So this is the flow. Say the flow of goods. Oh, that's really great. You have a flow of goods, but who cares? If nobody cares, it's like a tree in the wood who falls and there's nobody to miss it. There's just some stuff flowing, you know. And then this measures your people's desires. This is how much people care. Now, if there's a bunch of people walking around caring, that's not going to do anything either. You just sit there by yourself caring, Huh? So what really happens, something serious happens, if you get a flow of something that you care about, or you want to get rid of. Huh? Now, when you pair these two, right, then you're going to notice something happening. Then you have trade. Okay, that's economic activity. Okay. So for trade to happen, two things have to occur simultaneously. First, there has to be some flow of goods, and second, there has to be a difference in the amount each people cares for this flow of goods, right? There has to be a desirability drop. It has to go from the one who finds it less desirable to the one who finds the goods more desirable. Otherwise, still nothing is happening. You're just turning the stuff around. Okay? Huh? Right? Huh? So you see the same pairing showing up. Now, what we'll say is that this is a way to generate benefits. Okay? So economic benefits are something you can really enjoy. And that you do by having both a flow of goods and a desire to get those goods that has to be fulfilled. All right? Huh? Okay? So let's go and let's work this out, and then I'll come back to the rest of this table. So I first want to lay this down. All right, so these are just some summary slides. Huh? So here I worked it out. So you have a force and a velocity, you multiply them. So what is this really? Well, you can say this is really a force that you apply over a certain distance, right? Huh? And if I write that out, it's just this, and all I did was drop the dt. Okay? Huh? All right? Huh? Or divided by the dt. Okay? Huh? All right? Huh? So we would say that's an amount of work. This is an amount of work that was delivered, was done. And if you divide by dt, we would say it's the power that is delivered. All right? Huh? Now, in economics, you don't really deliver benefits, all right? Huh? You allocate them. So what happens is that if we look at the system and I'm trading with you, I'm not delivering you some benefits. No, the benefits are being allocated from me, which is the benefactor, to you, who is the beneficiary, all right? Huh? So you can think of power as this flow of energy, huh? If you want, boy, I haven't talked about energy yet, Let's just keep energy out of it, right? Huh? So that's a good way to think about it, okay? Huh? Now, if you do that over some time, so I'm allocating these benefits here at a certain rate, So I'm going to sum that up. So I have a total amount of benefits that I've allocated. And for the person who's on the receiving end, that's the benefits received. All right? And we would call that the work done, right? On this other object. Huh? Okay? So the thing to realize is that it all starts with benefits. Okay? Now there are various treatments of mechanics where this is your starting point, benefits, and then you take various derivatives to find out that you can write it like that. That's not the Newtonian approach. That's the Hamiltonian mechanics. Okay? And we'll do that later. Here we've done it the other way. We've kind of guessed the right thing called force, then we've guessed this one, and it all works out this way. All right? It's this nice product. Now, when I write a product, that will be a regular product when you're in one dimension. But in multiple dimensions, you got to be careful, right? So here is my quantity demanded. It's a vector. And here is my desire. It's some other vector. We'll have to see, it's some force laws or whatever. Huh? And I can't just multiply two vectors. Okay? Of course not. You got to decide, well, how do you do that? And there are different ways of doing it. The inner product, the outer product, cross product, blah, blah, blah. What you need here is the inner product, right? Because then you get a number. So, why the inner product? The inner product gives you the projection. And so you look at how much of this F is on here, right? And then that tells you how much you're pushing that way. If the designer is pointing the opposite way, you don't care about this guy. He's caring about movement. The benefits delivered in another direction. And, it's not going to. It's not going to accrue any benefits in this way. All right? Okay? Now, there's various ways of thinking about this. And one satisfying way is to see this inner product. So this is an inner product, right? So you can write it like this if you really want. If this is vectors. Well, sometimes people write it like this, with a dot. I'm going to leave that out. It just gets so, I don't know. I just want you to fill that in yourself. So this I find a really nice way of thinking about it, right? So you have these, you start off with these desires, right? So I want this. Now, the whole thing is you walk around with these desires, and you can, what you could do is imagine that you're, what's his name from the Rolling Stones? What's it saying? Big Jagger, yeah. So you imagine you're Big Jagger, thank you. I can't believe I blanked out of that. So what does Big Jagger tell us? He couldn't get any satisfaction, right? Now, he's been clear about this for a while, right? People have replayed this statement. So what's happening is he has a desire for something, and he's not getting a flow in that direction of his desire, right? So the poor fellow, he's sitting in a situation that whatever his desires are in the flow he's getting, this is zero, right? So these are orthogonal to each other. So this is Mick Jagger's situation, right? I think he's just saying it because I think he got a lot of satisfaction out of saying that he didn't get any satisfaction, because the guy has done really well for himself, actually. He's one of the few who's retained all his money. He's got a pile of cans, and he still spends, but he can't get any satisfaction. So maybe it's not quite accurate. So, but anyway. So the idea here is that you can also say, in a different analogy, that your desires are met by this flow, right? So you have these desires, and you're sitting that, and you see it more as a potential drop, And these are met by some flow. This is more the electrical engineering way of looking at it, right? Here is the force that is satisfied, right? So this is a flow, and it sits and it satisfies this, this like, I mean, you can think about this, quite subtly and see that there's differences in perspective, between the two analogs. I like this one. It's pretty clear. People also sometimes say that the needs are fulfilled, but we know that these needs, they, like if you have gravity, you can really, that the force is related to your needs, so you can just pull that in, and then you will say that these needs G are fulfilled by this flow. Huh? Okay. I like to think of needs as an acceleration, because it's about the goods, not about design. Anyway, these are just some colorful ways of thinking about how this concept of power applies. You see? And one thing that strikes me when you just sit down and relax about it and think, and this is also natural, right? Of course it is. And if I think of electrical systems, it's way less natural why the product of a voltage with a current should be power or something. Okay, right? So this is always, No, it's nice. This is also, the way you define energy is first by defining what work is, and I've decided to do the same thing here. And I'm very happy with it, because I think if you look at human evolution, it's pretty old. 30, 40,000 years ago, they were just hunting gatherers, but this stuff all applies to them. They still have desires. They have to get some berries to eat or whatever, right? And they would be satisfied. And you can just see, you don't need an economy for this. This is just fine, okay? This is just fine. Anybody can do this. You can even describe an animal with this kind of thing, all right? So the benefits that they acquire through their work or something, it's just, is that power, and it's just there. No matter whether you have any economy. So I would say this predates any economics. The part that doesn't predate economics is the calibration of this force on a price. And to have a price, you need a little bit more. You need a little bit more economics. Okay? And that's where I want to get to now. So let me go back to the list. And then I've done this thing. And I want to skip this for now and then move on to kinetic energy. All right? Now, kinetic energy, you see, the reason they figured it all out, this name kinetic energy, it comes from the 19th century. I think it was, I'm not sure who it was. Also Young or Rankin, or one of these types who were developing these engines, right? So it's all from the Industrial Revolution, when mankind was using the energy that was in steam and other coal and other things to start creating movement, Before they had relied on themselves or horses or maybe oxen to pull carts. But this is the first time that they get it from coal and other things. And there's a lot more energy in coal than there is in a human or a horse. And this is a big leap. But then they have to become pretty precise about what all these different forms are. So this is what is then kinetic. Kinetic means motion, right? So this is the energy that's in the motion. All right. Now, we will see that this is called the economic surplus. And there are two types of economic surplus, but we're the only ones who really make this distinction. But although economists make a distinction in direct and indirect surplus. So this is where I now want to talk about. Now, the surplus is something, economic surplus, that has not been with humanity forever, okay, like these benefits. I believe it was created about 12,000 years ago when human beings in the Fertile Crescent, where Iraq is right now, huh? And Iran and partially, Sumeria, those places. I think Sumeria is in Iran, isn't it? Huh? I'm not sure. Huh?
Mesopotamia.
Huh?
Mesopotamia.
Yeah, but it's partly in Iraq, partly in Iran, I believe. Huh? Somewhere there.
Yeah,
Huh?
same region.
Somewhere in the Middle East. So there was some people that did something brilliant. They took a blade of grass, okay, and there's these little seeds on there, you must know that, right? And they started cultivating this, and they made it into some humongous thing, okay? So these seeds were huge, and they could plant this everywhere, and then they would strip off these seeds and then process it and make bread, all right? So that is a huge breakthrough, because now you don't have to run around anymore and find some berries and other things to do. And they took a plot of land like this, and they put it full of these seeds. And then instead of running around, they would just sit here and then plod around a little bit. But they would get so much food, much more than they could eat themselves. Okay? And this is the creation of surplus. So before you do that, there is really no surplus. You're just only dealing with this quality demand, you don't have a price, you don't have anything, you just look at this flow, this V, your velocity, it's going on, and then when you need some, you start gathering a little bit more, a little bit less, but not too much, Although they did have some storage, that's an interesting thing. So they would store this, that's a little bit older than this. Okay, so the storage law can if you go to these museums or prehistory, I was in Greece and they have all this stuff, it's really old. You find these pots and from thousands of years ago, right? 20,000 years ago, I don't know. That predates farming. So they would do some little bit of storage law, right? But most of it was just. But here, this is when you first create something that's called the surplus, all right? So you have all this extra food that you can't eat. Now, what are you going to do with that? Right? I'll tell you what you're going to do with that. You're going to say, well, you get some guy. So some guy came along to try to steal this, of course. And he said, listen. This is not a good deal. You're stealing it because we get in a fight. You know what? I'll give you free food, and you just make sure that nobody else steals this. All right? So then you get some people who are just not going to waste their time anymore hunting and gathering. No, they're just sitting there sharpening their knives in order for somebody to go like this. Then, of course, it's a small step to grab the other guys. It's, these people sitting around anyway, right? So you go, a big army, you get everybody. So you got so much surplus, you don't know what to do. But then, you know what, your girlfriend needs, or your boyfriend needs something, now you want a nice little pot, so you get some other guys to make some pot, and then you see the whole thing goes nuts, all right? This is when you create surplus, but you need the surplus, all right? This is the economic surplus. So when people start eating vegetables, that's when we invent war and all of this. So all of war comes out of vegetarianism. Now, if you have economic surplus, you see, the point is, for the first time, you have something to trade. There was already some kind of trade, I understand, because there was a specialization between men and women. So there was already the concept in nature that not everybody was equal. Like most animals, all animals kind of old. The women, the females hunt, the males hunt, and pretty much the same. But humans, it was already distinct. And then they extended this to various classes. All right? And that's the surplus. This is going to make everything happen. So then when you have surplus, you're going to have prices at which the stuff can be traded, you're going to have markets, then you need people to protect those markets, so they sit in something called the citadel, to defend yourself, and then you have this whole area all defended and walled off, and then people live all together, and they have to find a way to live together, and they call that civilization, and blah, 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 blah. So everything goes around this marketplace. The rivers become important. And here in Holland too, we have all these names like Zandwijk. Right means market, huh? In English is Norwich, Sandwich is a Stanley marketplace, Zandwijk, huh? A Viking is also a marketeer, right? Handelaar, huh? A trader. Vik, huh? Weich in German.
If you have an electrical circuit without any storage, you never have a surplus because you're always expanding the storage.
Yeah. Yeah, so it's the pre-surplus days. So these, before agriculture, they had capacitors, resistors, maybe, right? And then, of course, external forces coming from humans, but no inductors. All right. Most of economic circuits also don't have an inductor. If you look at them, they just go boom, huh? Okay, huh? Yeah, that's the critical addition. It's the law of demand and the addition of the inductor, right? See, the inductor, what does it do? It couples magnetism to electricity. That's the brilliant thing of the inductor. And before you couple magnetism with electricity, you don't really have electromagnetism. And you certainly don't, you also don't have electrodynamics because there's no way to get dynamics. Well, you only have this silly dynamics where everything just kind of settles down. All right? Huh? I mean, what mechanisms can you build without masses, without inertia? Right? They're very limited. Huh? And they only live for a short period of time. Huh? You can't get oscillations. Huh? No, it sucks. So, yeah, so you need this demand. So this is the economic surplus. And so this happened like 10,000 BC or something. This happened, what, 1800, huh? 80, huh? 1800, huh? You know, to the 1900s, they kind of figured this out, huh? 19th century, how to control this. Now, energy is the same thing, right? So energy, what is energy? It's something you can do with what you want, that you have extra, right? Huh? You can turn it into light, you can turn it into heat, you can turn it into whatever you feel like. Huh? And that's the same with economic surplus. It's food you have in addition to being able to sustain yourself. What is, huh? So it's stuff you can get in addition. All right? Huh? Okay. So with that little background, let's now make it precise using the Newtonian method. But I first want to lay down this intuition, right? Huh? That the economic surplus is the same as kinetic energy from our economic engineering perspective. And that they both coincide with huge revolutions in human. Huh? So economies are born when surplus is born. Before the surplus, you just have these yeah. There's not really an economy because you don't have any price. Huh? Okay? And industry is born when they figure out how to generate kinetic energy. All right? And you can build a car. Otherwise you're walking. Or at best, riding a horse. Huh? Or getting somebody else to carry you or something. All right? Yeah, so I find this compelling. You know, there are two big revolutions, and we all know this, right? It's changed everything. It's hard for us to adapt. Of course, we've always had trouble adapting to civilization, right? So all the conflicts, politics, you see it now, it never is really comfortable, right? So there's all these periods where romantic people feel that they should go back to the old romantic lifestyle where everybody's happy. That's not true. They were always hungry, even then in the store. And, so I think as soon as, and it's too late for us. We're too adapted. We won't even survive. Huh? We won't make it. I mean, you guys won't even survive without your phone. I would be able to do that. You can't even do that. So here's a picture. I want to come back to that too. All right, it's just in the book I put everything in the beginning of the chapter and then I explain it. All right, so we did this already. So now let's go and explain what the simplest is using the. I'll do it in 2 steps. I'm first going to like plop it out there the way Marshall did it, and then I'll derive it from our definition of benefit, allocated benefits. All right. Huh? So this is Marshall's original graph, right? Huh? So he has a demand line and a supply line. They're a little bit different. Huh? And he calls it, you see, he's got this thing sloping up and this one sloping down, but you can imagine that if you flip them, right, suppose here's your 0, and this axis is the wrong way, you flip it, they'll both be here, right? Huh? Okay. He calls it rent. Nowadays, so rent was something they considered to get in addition to, what it's really worth, which is free money. Okay, that's not quite true. So now we won't do that. We'll call this the surplus area. Okay. Huh? And this will be what he calls the expenses, and that's usually called the cost now because accountants make a difference between costs and expenses. We would prefer to call this cost now. But those are details. But you see here what he's suggesting. And if you look at Wikipedia or something, they'll have a picture like this. Producer, surplus, consumer, you see the radius sign. Huh? So in the unified demand line, we'll put a 0 here. We'll run this axis the other way. Huh? Or this one. Huh? I don't care. All right? Huh? So it's this area. Okay? This area here. Now let's look at our own demand line, right? So here it is, okay? And let's look at this area here. How much is it? Well, that's pretty easy. That's a half. That's what this is, all right? Huh? How do you see that? Well, you know that this line, this is here. This is V, is P divided by N. It's kind of weird because you're going to look like that, so you integrate over P, so this is a dP, right? Huh? And then you do V dP, which is P divided by M dP, and then you integrate that, and you'll get a half mP squared. Huh? Usually you guys write this in terms of velocity, but I don't want to do that. Because it so happens that it's equal to this area, which is a half mv squared, right? Huh? Okay? But I don't want to do that. I'll get to this derivation later. I just want you to accept that this area is a half, and look, the whole area is P times V, right? Huh? And that's P squared divided by N, and you need half of it, so there you are. Huh? Okay. So, just by comparing this and this, you already see that Marshall's idea of surplus must be kinetic energy. All right? Okay. Huh? If we're to take this seriously. So we're in good company here. Things are going well. All right? Okay? Now, this is something that's always confusing to students because you've learned that kinetic energy is a half mv squared. And it's not. It's called the co-energy. But if you have a linear line, a demand line, then these numbers are equal. So you can switch them. But it really makes no sense because energy is something that's stored in something, okay? And the velocity is not stored. Momentum is stored. So it cannot depend logically on the velocity, you see? The other thing that's a problem is that velocity is not a phase variable, and it's all defined in Newtonian Mechanics, so momentum is a phase variable. So the other reason you know you're in trouble is because if you have light, the mass doesn't even exist, and it goes like this, and the kinetic energy is this area above All right, so you get in trouble when it's not a linear line. And in relativity, you're in trouble, okay? But it's just, otherwise you're not in trouble. So this is called the co-energy. Now, and then you have another relationship that says that the sum of these two must be equal to P times V. All right? You can see that. That relationship is called the Legendre transform in mechanics. But in economics, it has a nice implication, because what is this P times V term? You just take the flow and you multiply by the price. So those are just your expenditures, right? Or your revenue, if you're going the other way, right? So this is the revenue, this whole area. I subtract from that my cost of this area, and then I get the surplus. That's the easiest way to think of surplus, all right? So let's detail this now. So this was just kind of a guessing game as of now. We took this picture and placed it here, and all I did was kind of fit it in. And what I want to do now is really go through the derivation and see that this is the only thing that makes sense, okay? So we know what these benefit allocations are, the power, right? Huh? Those are the benefits received. That's equal to the desire times this flow, right? But now we have this demand. So this desire, what is it equal to? Well, it's going to be equal to the change in price, okay? All right? Okay? So it's the change in price times the flow. And what is that? And the way I'd like to see this is the change in price times the flow. If I do that times dt, then that will be equal to v times dp, right? Huh? Okay. Yes, why? Because the rate of change in the price over an interval dt, that is the price action, right? It's an infinitesimal amount in which you increase the price. You see that? Huh? All I'm saying is P now dt is dp, huh? So the rate at which the price is changing times dt is dp. This was an inducement, right? Huh? In mechanics, this is the impulse of the force. So the inertial force acts over a period dt. Huh? Now, this little thing here is dp. All right? That's a small raising of the price. That's done at a level of demand V. So this area here is precisely VDP. Okay? Huh? You see that? So then, if I integrate these sides, huh, I get that the amount of benefit transferred is equal to 1 over 2m p squared, right? Okay, so I'm just adding up all these areas. Huh? Little rectangles. Okay. Now you could say this is graphically all very simple, but the point here is that I started off with benefits. That's all I knew what was. And the only way I was able to get some kind of function out of there, right, was by doing this little trick. All right? So notice I didn't end up here. This is what I did. Okay? That's why this is called energy, all right? Because this thing is precisely the total amount of work that you've done, not this. So had this graph been like this whole derivation would have been correct. But this one, it wouldn't have given this area, all right? Huh? Okay. So how do you interpret something like this? A VDP. Economically. Well, what's happening is there's a flow of goods going at this rate V, right? And I multiply it by a small increase in margin, price margin. So that's the extra amount I'm going to make, right, due to increasing my price margin. So my real price is right here, and what I just did is I jacked it up above what the minimum is that I'm willing to let it go for, okay? You see? So this is an infinitesimal amount of profit I just made, right? Huh? Okay? And then I start doing that at every location on my demand line. So here I'm at level V, and I just jack up with a small margin, huh? So this is my margin, right? Huh? Okay? And if I do that over the whole demand line, you can see that all of this is profit. Okay? Right? Huh? So these are all benefits I just get. You know, are coming out of nowhere because people are willing to pay more, right? So what's happening, people are willing to pay this, and I'm willing to sell this one for a lot less, that one for a lot less, etc. Okay? In fact, what am I willing to sell it for? Well, when I'm at demand level V, then what is that's my price level. So these are the costs associated with getting rid of this thing, okay, for me, right? That's the price I assign to it. I extend the demand with a little bit dV, so I'm going to, the supply in this case, I'm going to give you a little bit more. So the total amount is PdV, right? Okay? That's my cost to me, to let it go. Of course, so I'm going to get that because my total revenue includes that, right? But I'm going to charge a little bit more. I'm going to charge all this more, right? Okay? So this is what I get in addition. That's my economic surplus. Okay? This is how they figure this. So if you integrate this thing, then you have to express the price as a function of the quantity demanded. Well, we know what that is. That's m times VdV. And now you get a half mv squared. So you see this one, you integrate along the quantity demanded. So you're going to get a function of that, the flow, right? And this thing you integrate along the price margin that you keep upping it with, right? Okay? So this is going to be a function of your price. So as a person who's enjoying this thing, of course it's going to be dependent on your demand. But if somebody's trying to sell it and get rid of it too much, it's going to depend on the price you can charge. You know? So here you see the difference between the economic surplus and the economic costs. All right? And the way an economist will do that is using these kind of graphs. The way we do it is just with the formula. We don't like these graphs. Okay? We just integrate it out. Now, this is called in engineering or in physics the work energy principle. So it means that work can be transformed into energy, and energy back into work. All right. So you get this. This should have been T dot, of course. That the work you do on a mass increases its kinetic energy. All right. This can go the other way around. The kinetic energy can end up doing work, and it's called the work energy principle. And what I use here is I call it the work that benefits, and energy is the surplus. And I call it the benefit surplus principle. Okay? So work is something different than energy, right? Work you do is a process. It's like heat. Energy is stored in something. Okay? Huh? Right? Huh? So surplus is stored. You know, you have is my surplus. It's surplus. And I'm transferring the surplus, allocating the surplus to you. All right? Huh? So what we're doing in these economies post-agricultural revolution is moving the surplus around. I have the surplus of this, but then if I move it to you, then you have it, and then you do it, and you do it, and we're just trading the surplus all over the place. All right? Huh? Creating surplus and then trading it. Okay? So that's what you do. You don't really create it. You have to transform from something that's available, maybe a plot of land and the sun or whatever. Okay, but then you can then make it into something useful that can be traded. And it's the same with energy. You got to get it from somewhere, maybe from oil field or solar panel, sun with a solar panel. Then once you got it, you start like moving it around, right? Okay. So this will be the marginal cost, huh? And this will be the marginal surplus, right? So when they have infinitesimals, economists like to call those marginal quantities. I kind of like the word better than infinitesimals. Yeah, my writing is terrible. Marginal surplus. And these are the marginal costs. These are the total cost. There's a marginal cost. And this is, all right? So intuitively it makes sense, but also if you follow this work energy principle, you see you're stuck. You know, there's only one way to write this F is like this. So here's where we use Newton's law, right? Without Newton's law, we couldn't have done this step. You know, because we couldn't have written this force in terms of a price change. Okay? So Newton's law allows you to define the kinetic energy. So that's not how it went originally. They pulled it out of thin air. That's what Leibniz did. And then Newton used a momentum, all right, and didn't say much about energy. And then somebody later realized that you could just do this. Okay? So, but this is important, right, to see. You see, this fitting is nice and well, so that's just it. But this gives you confidence that this is on the right track. Okay, this law is important.
If you change your price without increasing the quantity, you're basically changing the angle of the demand line, right?
No. This is the minimum price at which you're willing to sell, right? Mm-hmm. Huh? But you just increase the price a little bit above that. This is what happens, right? So the demand line gives you the minimum or the maximum you're willing to pay, all right? Huh? It's also called the reservation price. The real price can be underneath or whatever. The real price, what is the real price? There's only one, huh? Okay? So this is a little bit confusing because the word price gets used in so many contexts. The reservation price, which is my price, ask price, bid price, blah, 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 blah. Real price, whatever that is, right? Huh? Okay. Huh? So the thing that Marshall imagined was that, okay, these are your prices, so they go along this line, right? But then there's a big market out there which is just willing to pay this, right? So you can sell to this market, right? And on the first item you will make this profit, and the second one you'll make that, huh? And then all from here and then you'll stop selling because now your price is the same as the market's price. So you'll stop running along. Huh? And what we would say at that point, P dot is, well, it'll have to be zero or something, right? But we'll have to figure that out with some counter forces. Okay? Huh? Okay? So there's all this work and energy, all it does is keep track of that. You see, if you look at a regular mass, there's kind of these two types of energy. There's this energy that is the co-energy just sitting in there, you can't get it out. It just has to be there. It's you'll see some text, people with papers writing about it. There was a guy in this department, doing all this research on co-energy and what it is. But it gets a little fuzzy, like why does a mass have this weird co-energy? The electrical engineers, they also use it like the co-energy in an inductor, But it's something that cannot do work. It's still energy, it has units of energy, but it cannot do work. Right? Huh? And here you see this co-energy, that's your cost. So of course the cost to you is just what it's worth to you. So you can't use that to spend freely because you're dying. You're not, Huh? See, it's incumbent. So it cannot do you can't do useful things with it, It's not available. You can, after lecture, go and look it up a little bit what co-energy is. You'll see there's all kinds of discussions. And they're useful for calculations, but you can't get work out of it. Okay? Now, what airline companies try to do, for instance, is they try to ride everybody along their demand line, right? So they don't like selling everything for the same price. So they'll see that the people who are willing to pay this, they'll have, and then the people only willing to pay that, they'll also try to give them a seat for that price, So they'll try to get all the surplus in their own pocket, and not giving the customers any. You just charge just enough that the person wants to pay for it, right? Huh? But don't give them any welfare, So that's what economists call, this is also the welfare, That's the stuff that as a consumer you get in addition because somebody's willing to sell it to you for less than you would be willing to pay. So the difference you can use, you don't have to need for subsistence. You can use it anything. You can book a trip or, give a gift. I don't know what you want to do, right? Huh? Okay, huh? And their idea is that this wealth, this surplus is what makes the world go round, what makes the economy work, right? That you get more than that you need. And that's also this idea of the agricultural revolution. Like, I think it's not good. The invention of agriculture, you get more food than you need, and then you got all this extra. You can monetize it or value it, and then move it around, and somebody else can make more shoes than they need. Huh? And that's how you create welfare. Okay. So we get all these benefits, now coming out of nowhere. Huh? Supposedly, of course they don't come out of nowhere. It's just that's the benefits of trade or the benefits of creating machines. Huh? Yeah, specialization gives you surplus. Same as same with energy, right? So you get the energy focused in one direction, and then it's specialized in this direction. When it's all over the place, and you have heat, you can't do anything with it, right? Huh? So it's good to spend some time talking about this because you gotta let it sink in, what this is. All right? Huh? Okay. Now, this benefit surplus principle is just great because you can use it to prove everything, right? So what I can do is take that same amount of work, I'm just going to talk first mechanically, that I put in that mass, and it was equal to that, right? The velocity times the change in momentum. But I can rewrite, if I attach it to a spring, right? And the spring will be able to counter that thing with a force. It's a spring force, okay? And that velocity is going to be the rate at which the spring is going to be contracted or extended, right? So I can take these benefits and write them like this, right? Okay? And this I call the potential energy, and I take the derivative, and I got this minus sign. That's okay. All right? Okay? So I play the same trick. You can also say I have this, which is that, which happens to be, f times q naught. And you need a minus sign, right? Because of the scarcity force and convenience, they act the wrong way. Right? So we did a little bit different. Instead of looking at a change in the momentum, we're now looking at a change in position. All right? Now, we can do the same in economics, right? Because we got our storage law. So we got all these benefits, but now you're going to store them. You store the goods. So what's going to happen to this flow? Well, you're going to store this flow of goods, right, in the spring, in your storage. So what's going to do? It's going to increase the level of the storage, well, at this rate. Okay? So now Q is not just the balance, it's actually the amount you have the storage. Okay? Notice that that's not what the quantity demanded does with the mass or with demand. It just sits and flows, there's nothing accumulating. Okay? What accumulates is price. If you apply a want on it, or force. All right? Here, what you accumulate are the goods themselves. All right? So you get the counter of this thing, right? So rather than thinking of the economic force as something that drives the price, P dot, you now think of the quantity, the flow quantity as driving the amount that you have in stock. All right? Okay? Now, if I calculate this thing, that is the same as this, right? And if I take a linear spring, then I know this is k times q dq, right? So there's a linear storage, and what do I get here now? The Lord be praised, just potential energy, right? Okay? So what has happened to our surplus? What has happened to our kinetic energy? It has disappeared. That mass is standing still, for instance. But it went somewhere. It went into that spring. So somehow that spring, now is storing this energy. And how do we know that? Well, because if we attach the mass, it just comes out again. All right? Okay? Okay? By the way, from this you can immediately see that T dot plus V dot is 0. And if you integrate that, you get the law of conservation of mechanical energy, right? So that's just an aside. So, first of all, using Newton's laws, and here we, you also had to use this thing, right? The definition of stock. And Newton's laws, I get the potential energy. Now let's look at it from an economic perspective, okay? What's happening here? Well, I kind of wrote it down here. So you see, you can look at the benefits of holding something, So what are those? That's F dq. Okay. What do you do with the storage? All right, so the surplus, if I look at this from an economic perspective, I have the surplus, and it just now goes into the storage. So all my surplus that I have in trade, so the kinetic energy is like the energy that's in the trade. I'm actually buying and selling because it's my demand. Now it's out of my demand, right? My mass is standing still. right? I'm not demanding anything. But somehow I got rid of it, and it's in the storage jar that I have, that I already had, all right? So my surplus is gone, but not really. It's sitting in there because when I want to start buying or when I want to start selling again, I can just take it out and give it to somebody, and I can generate trade again, okay? Also, when I'm short, I can just say, oh, I'm short, and I'll just go and start buying and generate trade again, okay? So these storage jars that they start functioning as a form of keeping a surplus. That you don't have to take your stuff to market immediately, all right? That you can have a grain silo on that field, and only once a week you go to market and sell this, all right? Huh? Okay? So you get all this stuff coming out, but you store it. And you're not only storing the goods, you're also storing the surplus. So storing the goods, that's upping your stock, okay? But storing the surplus, you multiply that by the desirability of that. That incremental stock up, all right? And if you do that over, you fill up your storage, then you get this thing that is sometimes called the indirect surplus, because the direct surplus, that's the kinetic energy. That's immediately tradable. Kinetic, trade, demand, that's all the same thing, movement, right? This is potential energy. There's potential to be made into real surplus, right? So you can call it the potential surplus. Okay. Now, for this whole business to work, for you to do this integration, you better have it that this thing is a function of Q, right? Because otherwise, how are you going to integrate this thing? Okay. So you need what I would call as a conservative force. Okay. If you know Q, so your storage that you know how desirable it is, right? So if you know how the extension is of this thing, how far it's moved, then you know the force it gives you. All right? Now that's a spring, right? If you know it's here, okay, it's there. But a damper doesn't qualify. It doesn't, because you know the damper's there. How do you know what force it's giving you? Maybe zero. It is. You have to go with the velocity, right? So you can't just plug anything here. This has to be, now an economic, this has to be the force of scarcity, or the convenience force, right? Okay? We also call these things conservative forces, and I like to call them convenience forces, all right? So what's going on here? Suppose I'm trading, and look at my potential surplus here, and then I go along this bottom, and then I look there how much I've got, right? So, okay, I can have a DQ, change in QB, and I can have a change in QA. That's no problem, because that's just the integral of dQA. But what about this thing, this integral f dq, right? Is that actually going to end up to give me a number here? Now, if you go along a path, of course it is. But what if I take another path? Will it give me the same number? No. If I have this, it would. But not in general, right? This integral, if you just do an integral like this, you just have some general force here. Right? There's no reason this should not depend on the huge distance you travel or something, right? Only when this is a conservative force, and this thing only depends on the position Q, will not work out, right? Okay? And if it works out, then you can get this function of Q that is independent of how you got there. You see, that's important to see. Otherwise, this function is pointless. It's not a function at all. It's just some kind of number you associate with a particular path. So if I take that friction force and I take the strength and I move it over here, there's a certain amount of work I did, but if I do it like this, there's a lot more work and I end up at the same place. All right? Right? Okay? But if I do it in a gravity field, then we'll go. All right? Okay? So you can think of this as the marginal benefits of holding. So there are some benefits of holding something, and that's one way to describe it. That's the work you have to do. So that's the benefits you have to pour into that storage jar, because that's going to give you not the total benefits of holding. So the difference between the convenience, which is a force, and the benefits you derive from having that in storage. Okay? But that is equivalent to the surplus that you can generate with that storage, the economic surplus. So we can also call it the indirect surplus. And that's the way of potential surplus. All right? So just think kinetic energy, that's the surplus, that's the profit. All right? And potential energy is something you can change into that, right? With your storage. Okay? All right? This is an interesting story, because these are very important concepts that have been with humanity a long time. And as engineers, we can look at it. I'm not saying this is the right way to look at it from a historic, from an economic or even a historical economic perspective. But it's interesting to see how this really clarifies, to me, as we talk all these concepts, how why they're important, and how you can think very precisely about this using the same tools that you're so used to. And for me, and maybe I've said it many times, it's sometimes amazing how much more clearer the economic implication is than the mechanical. Only you get used to it. It's the spring, spring force, spring potential energy, but whatever, right? Okay? But that your storage contains stuff, not only an amount of stuff, right? That's the integral of what's in there. But also this integral, right? Huh? Okay, the benefits that are associated with it. Huh? So a capacitor not only has a charge, but also the electrical energy that it stores. All right? Huh? And the fact that you can calculate this integral is independent of how that capacitor did it, all right? Because this thing is going to depend on the charge, right? Huh? Okay. That makes this a real property of the capacitor, okay? And the fact that if you look at your storage jar, you just know how much is in there, and then you will know how much the surplus is that you can get it, and that makes it a property. It's not to make these storage jars so useful, right? The fact that you can assign it that number, you don't have to ask how did he fill it up, right? It's the history is not important. Okay, it's very, very useful. That's what that makes or breaks these concepts. Okay, and of course it all uses this one little feature here and this feature right here. You'll know that we've had. Okay, and you pair them, and you know all the relationships, so you know that this is a function of Q for spring, and then you're running. Huh? This is the game. Now you would say at this point, we're kind of run out of ideas here because we have this work rate and it's this. Now you can either write this as P naught or either write that as Q naught, but now we're kind of ran out of ideas. And in a sense, you're right. In a sense, you're right. That's about the two things you can do. Kinetic energy, potential energy. There's not other stuff. All right? Huh? Okay? So that's when you look at a Lagrangian or Hamiltonian analysis, that's all they've got, right? So the mechanical energy is this, the Lagrangian is T minus V, it's actually the co-energy, right? So in a sense, that's the end of it, right? And the bond graph too. You know, you have these power bonds. So the bond graph is actually a nice thing. You guys have done that. I wanted to do after this series of lectures, I want to do a short one on bond graph. But there you see you have a 1 junction and a 0 junction, you have an I element, and you have a C element. Now what happens here, this is where the energy gets transferred. There's a power element, so there's a force and there's a velocity, right? So this thing tells you how the surplus gets allocated, okay? Right? Huh? So you can put a resistor here, we haven't done that yet. And then you will see that this I element will allocate, you know, this thing distributes the surplus among these elements, right? Huh? And these I and C elements are the surplus storage elements, right? So it's the energy storage elements. So bond graphs are nice because they show the flow of the allocation of the surplus, right? So this one is allocating surplus there, this one is allocating, okay? And these bond graph arrows, these half arrows, tell you who is the benefactor and beneficiary. All right? Now, it can be negative in reality, but this is just a choice. Huh? Yeah. All right? Huh? And in fact, if I did this, right? Huh? Then here, you'll see a Q dot and an F, and here you'll see a P dot and a V. I always get mixed up, right? Okay, so you clearly see how cleverly, you know, here the quantity demanded goes into increasing the storage here, huh? And here the force goes into increasing the price of your element, huh? Okay? And I think what they do, they have here this I element, huh? And then they'll plot they'll say this is K and this is M or something. I forget how they do that, right? Huh? But they'll tell you what the constitutive equation is, huh? Okay? And then you see this thing is allocating or reallocating a surplus. This is going, you get it out of your storage jar, and you sell it, then you go, oh, I got too little, and then you buy some more, put it back in your storage jar, and you're a loss later, right? Huh? And you keep allocating surplus between your trading operations and your inventory, okay? Huh? So they're nice in this way, okay? If you just make an electrical circuit or my diagram, it's very hard to read off how the surplus flows. Right? So I made an attempt here. Let's see. We'll have to do the damper a little bit, but you know there's surplus here, and it's flowing out, and it's flowing into this thing. It's an attempt I made in the paper to show you how the surplus gets allocated. And then I put all in here. Okay. This one can go the other way, but this one can only go one way, right? We'll get to that. Yeah? We'll get to that. Okay? So these bond graphs are going to be really great for dealing with energy flows, right? The different ways of reallocating benefits. Okay, so we ran out of ideas, but we still have one more element left, you know, this, which is the damper, right? And we looked at this damper as something that causes economic friction. And we have two types of economic friction. Either the trade friction, so that is that what happens is it's some kind of intermediary, and what he or she does is impedes the flow of the goods, okay? That's the same thing what a resistor does in an electrical network. It impedes the flow of current, right? Okay? And the other one is that it impedes the communication of the watts. So that's when you put it in series with a capacitor like this. All right? So this store wants to communicate the watts from this place to there, and The higher this B is, the better it can do that. All right? So with inverse B, so 1 over B, actually, 1 over B impedes it, right? So if there's no damping, then it cannot communicate its bonds to this. This is a mass to this mass. All right? Huh? Okay. Now let's work through it. As always, we use the benefit surplus principle, the energy, the work energy principle. So I start with the surplus now from the demander. I write it, of course, like this. Okay, the rate at which it's being allocated. Now I know that this is equal now to the friction force. And the friction force is a function of the flow quantity, because this is some handler or broker or something is going to charge his cut, right? So his incentive is a function of the flow he's handling, all right? And he's impeding this, so I need the minus sign, okay? That's my assumption, the way I set it up. All right, so he needs to be incentivized. And this thing is what we call, this product here, that's the power. That's what we call the real power. Okay? So if I looked at the bond graph, and I have an I element here, this will be an R element, and then the power will be on this block here. Okay? Huh? And one thing you have to realize is that this power is always bigger than 0, so negative of the power is smaller than 0. So that's different from T dot, the surplus and the other surplus. It can go either way. You can take it out of storage, put it in storage, you can demand, you can supply, but there's only, your intermediary is just going to charge you money and that's it. Huh? It's not going to give you money to do the services. All right? Now, if you have a linear damper, you will get this law here, right? So you'll see that the surplus you have to allocate, the surplus allocation rate goes with the square of the flow. Why the square? Because this guy just needs more and more, that's just our assumption. So that rolls out of a linear, when you get a linear. All right? Huh? And the other way is that you have some kind of storage, but things are just leaking out, right? It's just, the storage jar is not really great. So that means that this 1 over B I should put here is not 0. Okay? So what you need here is 1 over B to be 0, or that the thing is infinitely friction, all right? It turns the other way around, because you'll see all this, here the force is 1 over B, here it is. So this constant here is the inverse. It's a little confusing, but you know. So if you have a storage jar and it's perfect, you're going to have, this thing is just bar, right? And it's going to maintain its surplus forever, right? You will come back and all the stuff is in there, and nothing is stolen, nothing is evaporated. So that's why I like to think of this as a sort of a custodian, right? It's the thing, and he or she is not taking out of this, right? So you got the same kind of thing. We just applied a benefit surplus principle. You'll see this is another way of losing surplus. But all of these are positive. These p's are positive, right? Look at it. Those are the square, right? This is a positive number. This is a square. It's got to be positive. So, so that means this thing is decreasing. So your storage jar is not going to give you new surplus, I don't know. And neither is your broker or the guy who's driving the stuff to market. He's not going to show up with twice as much at market, all right? This is a big distinction, right? And what does that really mean? That means that there is a sort of direction up to time that's irrevocable, you know? Because of you see, if you just look at storage and demand, everything can go every which way. Buy, sell, turn around, turn blah, 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 turn time back, no problem, right? But as soon as you have some infrastructure, right? So you're not just sitting there hiring your own guys to go fight for you, but you have some intermediaries, some placement office, or you have people who go for you to market and all of this. That's when you start getting frictions, right? Trade frictions, storage frictions, or, all this kind of stuff, right? So that's the whole infrastructure that grows up of intermediaries and grows up around these surplus markets, okay? And they give the direction of time to it. All of a sudden, you'll see that these systems are, time starts playing a role because all these effects, you see this V dot, I can integrate over dt and we get a function like that, right? Why? Because q dot dt happens to be equal to dq. But no such luck here. If I integrate the power dt, there's no way of saying there's a function, whatever q of t, that it's only a function of t. It doesn't work. This doesn't work. So you only get some delta q here. This is some number associated with a particular way you arrange for the transport and you arrange for all these things. So it's very path dependent. Okay? You see? So if I go back to this picture, you'll see that for those frictions, it very much depends whether you're shipping all this right now and then blah, blah, there's some optimum. Okay? So this is an interesting thing, right? Because suppose you just had this system here. It's exactly what you were suggesting of it. There is definitely a direction of time. We all know that what it will do, the prices just drop like that to zero. Okay? And this thing also, we also know that the storage level is just going to drop to zero ultimately, right? Or some level, okay? But what if I have this system, right? Well, it will just oscillate indefinitely. And I can oscillate backward, forward. You will never see the difference, right? So with just storage, surplus elements, retaining elements, you don't have time really. You can go every which way. You can run the economy backward, forward. Everybody buys, sells, It's just one big circus, okay? But as soon as you introduce this infrastructure, then time starts playing a role, all right? Then you have to get things like interest rates, that things tomorrow are just different than they are today because of all this friction all around you, and we'll have to account for that, Okay? Now, there's a quote by Adam Smith that is really very famous. It's called The Invisible Hand. And here it is. They are led by an invisible hand to make nearly the same distribution of the necessities of life which would have been made had the earth been divided into equal portions among all its inhabitants. Okay? It's a very famous quote. It's called The Invisible Hand quote. And Adam Smith has been quoted on this, and misquoted on this, and double quoted on this, saying this means that all economies always come to an equilibrium. And that's the basic idea. All right? And what I want to do is dissect this quote from an economic engineering perspective and show you that he must, if he refers to something from our perspective, he must be referring to this. Okay? So, in order to do that, and I think this is no, it's not my last slide, but I want to do this anyway. So we may have to finish this next week. So you can ask yourself, okay, what happens in the damper, right? So here's a damper. So I draw them like this, right? Huh? I draw them like that. Really what happens is this thing is closed here, and then there's a little like opening here, huh? And then there's oil everywhere. And then when you push, this oil gets pushed through there and it goes every which way, right? Huh? Okay? So these oil particles are standing still, they're not, of course, because they have a certain temperature, but assume. And then when you come there with a damper, what's happening, these oil particles, you can imagine these little billiard balls made up of little tiny balls. Right? They go through there and they'll be flying around every which way. And as a result, your speed here is significantly reduced, right? Somehow you lost energy, right? And it all went into, so what comes out of here is going to be slower than that. It's going to impede that flow, all right? Now what happens, okay? So what has happened is, suppose you have a certain amount of kinetic energy coming in this thing. The kinetic energy hasn't disappeared, but what has happened is, it has imparted that kinetic energy to every one of these particles. And because these particles are bouncing with each other in very weird ways, they're not shooting everywhere. But if you add up all the kinetic energies of every one of these billiard balls, you're going to find exactly the same number as what you had in this one huge thing that was pushing it to begin with. Okay? So the law of conservation of energy that follows from Newton's laws will hold. But something happens. Okay? So if this damper was not there, then whatever mass would have been here would have received all the kinetic energy. But now that's not the case. So what happened here? Now, what happened is something we call dissipation. Right? So what dissipation is you take that unidirectional kinetic energy, half MP, half 1 divided by 2 mp squared, where all the momentum is a vector is pointing in the same direction. And then you dissipate it. So that means you spread it out over all these particles that have all different vector momentum. Okay? All right? Huh? That's why you see that the final momentum coming out of here has been gone, but it's just been dissipated. All right? Now, there's actually a name for this degree of dissipation, right? It's called entropy, okay? And the conversion from entropy to the amount of kinetic energy that went in there, that's called temperature, all right? I mean, I don't want to get into that, but this is what's going on, all right? We'll get into this much later when we do thermodynamics. Now, let's translate this to the economic situation. What are all these billiard balls? Well, they must be agents, okay? So some big guy is coming in here and he's pushing all these people, and this one gets a little knock and it goes this way, this one gets a knock and they go that way, right? And everybody gets a knock and they start, this one may go up and you must start buying ice cream cones instead of the apples, which were on this axis, and there may be many more directions, all right? So all kinds of people are making little transactions with an enormous amount of goods, whereas we started off with one demander only making, transactions in one good, huge transactions, all right? And that we call entropy, right? In economics, we will call distribution or diversification. Distribution, when you distribute it out of the different agents, and diversify if it goes in different dimensions, okay? So you call it diversification. So the concept of distribution of surplus and diversification of the surplus, those concepts are tied to damping and dissipation. Together we call them dissipation. That's what's really happening. Okay? So you see, again, these things are magical until you just take the economic engineering Newtonian basis and you go, okay, this is what's called statistical mechanics, and ultimately this is how they figured out what entropy really was. So heat really was, temperature really was, because they made these kind of models and it seemed to work. That's Boltzmann's thing. All right? So you see this process, all right? Now, let's look at this graph. And the distribution of the necessities of life. All right? He talks about the necessity. I like this word distribution because that means we have lots of agents here. The necessities of life I don't like so much, because they're more than that. It could also be the surplus, right? But let's be the distribution. We can put surplus here, or benefits. Let's call it benefits. That's actually better. Those are the necessities of life, right? Benefits. Okay? But the earth been divided into equal portions among all its inhabitants. So if it was not one person, but everybody here, all these people making that infrastructure, had that, then you would, this is the invisible hand, all right? So I like this quote because it's actually possible to decipher it from a statistical mechanical point of view and then argue that the arrow of time, which for us is the creation of entropy, that always has to increase, okay, is precisely, what's going on in Smith's idea, all right? So those are the frictions and the damping, the frictions, economic frictions that are causing this invisible hand. So the invisible hand is not the forced equilibrium, but it is the sort of entropy death, right? So that everything is generated into heat, and then you got to get the whole thing going again, right? And then everybody starts distributing it out and making their welfare economics and giving everybody equal portions, and then the whole thing stops, right? I mean, have you ever seen a poor man hire another poor man? Right? No, right? As the old saying goes. So you need somebody with a lot of money to get the economy going again. All right? So those are the famous quotes. I like these things because it gives us time to reread this. So the idea of dissipation is that everybody gets his pro rata share, and the energy is distributed, the surplus is totally distributed. I like to add these dimensions to it, and also modern people thermodynamics do that. And it's another sort of chemical, another potential. In thermodynamics, there's only three, so it gets boring, but we can have D, and then we can spread it out over a whole portfolio. All right? Okay. Now here is a picture that kind of summarizes it all. So, I put this picture in to kind of show you the difference. So here you see how the indirect surplus can change, and it increases. So if you had a demander with a demander and a storage, then you see the increase in this is going to lead to a decrease of the direct surplus here, right? Because you need to have that V P dot equals this, okay? Then you have conservation of energy, or power, balance, okay? So you get that T dot is equal to minus V dot, right? Or T dot plus V dot is 0. And if I integrate it, then I can get that this sum, which is sometimes called the Hamiltonian or the mechanical energy, right, is a constant, okay? But what you got to see is this can also decrease. So suppose it went like this, then this thing has to increase, right? So you can see them going like zoop, 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 So if you have a demand line, you can see this, around the equilibrium point, it will not settle there if there's no friction, right? So if you make one of these economics demand lines, and you're here, it will go down, but if it's a storage, it will just keep doing this, and the other guy will go like this, and they will just keep oscillating, right? So you'll need this friction in order to actually converge to this one point, okay? We'll show this later, okay? So economists, when they say equilibrium will be achieved, that's only because they always assume that this invisible hand must happen, and therefore there must be friction, otherwise it's going to oscillate. Okay? Yeah. You know that the energy will eternally go from mass to kinetic to potential if you don't have damping. All right. And here, the surplus will be allocated either to your storage or to your trading operations, and nothing will ever happen. This is, of course, not very practical. Now, this graph also shows you what's different about the dissipated surplus, because then you plot the force against the flow. And then this thing, and this is always positive. I mean, this thing can go either way, but this thing cannot, right? So when you connect this to your storage jar, yeah, this will always be positive, so this thing always has to be negative, and you'll end up with nothing. Huh? Same story there. All right. Now, why do I make these graphs? Because this is how economists like to look at it, and I'm trying to make that connection. Okay? Now, on the way to the forum, what we've done is we've proven this law of conservation of energy, right? So you know that this is unit, and then you can add this. This is just all the power, and this thing is a constant. This whole thing is a constant. This thing only goes up, and this thing has to go down then. And then you can add some benefits, and then you want to add that over there. Okay? And we will call that the law of conservation of energy. It's a weird law, right? Because you assume it's true, and then when it's not true, you just find it. You take, well, the amount that's not true, and you assign it to something. So you always be sure that it's not one of these laws that are just by definition true. Now, economists will never talk of conservation of surplus, okay? And the closest concept they will have is that of allocated efficiency. So they will say that if you reallocate the surplus, you're efficient if you do this dollar for dollar, right? You can ask yourself, how can you have allocated inefficiency then? And then the way we look at it, that's really not very possible, right? I mean, you could say, well, I will leave this out, so then this is the inefficiency because this is what I have to keep putting in, but this is not how we look at it, right? This is how they used to look at it. So, in the old days, I mean, before Joule, they figured out, like that story about what mechanical energy was and how you can have potential and kinetic. But heat, just the dissipated energy was something else. They didn't think of it as energy. In fact, the first was measured in horsepower, where you used the work energy principle. So you looked at the power delivered by a horse. That's what Watt did. And then he calibrated the kinetic energy with that. So he says there are so many horsepowers, and the engines are rated still in horsepowers. And then types doing heat, they didn't use horsepowers, they used calorics. So we still measure it in calories. Calories just means heat in Latin. French is chaud, calor. So these are units of heat. And it was just, so this Q, this kind of got lost because this gets converted to heat, right? And then you cool it, and then you keep it off. So this got lost, and you saw this thing, the mechanical energy just go down, right? So in that sense, you could think of this thing as allocated inefficient because you're losing this. So the friction brings in the inefficiency, right? But sometimes you want friction because you want to heat yourself up. So you can also say it's efficient, and this is just another form of energy. And this was done by Joule, right? So he took this big container and he took a paddle and he started turning this paddle wheel like a maniac. And then it just warmed up, and all the kinetic energy that was in the paddle that he put in was gone. And then he measured how much the water was heated up, and he says, well, that's now the caloric equivalent of this, was a brilliant idea. So what he ended up doing is just plugging this thing back in and making the balance come out. Then they found other problems. and then they plug, electrical energy, and then just keep plugging stuff in. So the way we approach it now is very different. We always assume that you don't make a difference about efficiency, inefficiency just at the outset. You would say like, okay, I'm interested in having as much of this as possible, or as much of that as possible. I'm making a heater, or I'm making a light bulb, and then you will change your notion of efficiency, but it's not. And then maybe you could call that allocated, more efficient, also in economics. All right, so it's a little bit of a question mark on exactly how to do that. Okay. All right, I think the time is up, and unless there are really burning questions here, we probably should wrap up the show. So I hope I've given you a nice first look at how energy and surplus and work and benefits relate, and how we can use this machinery of Newtonian mechanics that we've done in our theory of demand to derive it all, make sense out of it all, quantify it all, and also provide the intuition. All right? So we'll come back to this next week, and then maybe there'll be some questions then, but at least we're able to finish it. Okay?